Okay, so welcome back to another video. So in today's video, we actually have this little equation: y is equal to the base e of the log of x over m minus s times a divided by r squared. So this is a pretty standard algebra problem. So what I can do is I'll just multiply r squared to both sides. So then we'll get y times r squared is equal to log the base e of x divided by m minus sa. Okay, and then I'll just take the e base to both sides, so that we'll get e to the y r squared, and the logs will cancel, and so with that, so we're just left with just our input, which is just x divided by m minus s times a. And how about I'll actually multiply the m to both sides so that the denominator from here will cancel. So we'll get that this is m times e to the y r squared, and that's equal to s MAS. And then how about this? I'll just expand this out a little bit so that we get this is m times e to the r times y, and then equals to x minus, like so. And there we have it. Nice. Okay, so that was obviously quite a short video, so obviously nothing like with a length like that, that's never going to go on YouTube for me personally. But, you know, if you haven't looked at the date, it's December 25th, so I'll just start off by saying Merry Christmas to everybody, all the viewers, anybody watching this channel, or pretty much all my friends or families. I know that this is kind of we're going through a rough time, especially with the pandemic. So especially with that consideration, it's very difficult to see, you know, our loved ones, our relatives, anybody living long distance or even short distance rather. So, but it's in reality, it's really difficult to like see each other. So I hope that we can get through this, and I hope that everybody has a blissful day. And I hope you guys get like some money and presents out of it, so that's nice. I know I did. But anyways, just once again, I want to reiterate, just saying Merry Christmas to everyone. I hope you all have a great rest of your day. Now, how about we actually get to the real video? Okay, so now the actual video. So now we're being asked to prove the following. Gamma of z multiplied by gamma of 1 minus z is equal to pi divided by sine of pi z. And this is actually special because this is actually known as Euler's reflection formula. And this is actually one of those very interesting properties with gamma functions where, you know, the gamma function itself is defined as, you know, the as a extension of the factorial function into the complex numbers. So really, the gamma of some input z is actually equal to, or rather, the gamma of n is equal to n minus 1 factorial. So we're taking that extension and converting it into the complex number system. So that's what it's usually defined. So, okay, so as I said, we're going to be proving this little property over here, this formula. So let's actually do this. So, okay, so let's actually use the definition of Euler's definition of the gamma function. So the following is that gamma of z is actually equal to defined as 1 divided by z multiplied by the product series, the infinite product series of from k is equal to 1 to infinity of k plus 1 divided by k to the power z, and then multiplied by k divided by z plus k. Okay, so one interesting property we want to note is that, and this will become very important for when we combine everything together using these properties, we want to note that the gamma function from 1 minus z, we can use the property of gamma functions that this is actually equivalent to negative z multiplied by the gamma of negative z. Using this, we can actually reiterate and say that the gamma of z multiplied by the gamma of 1 minus z is actually equal to negative z multiplied by gamma z, and then multiplied by gamma of negative z. Okay, so now let's actually just focus on this expression here. So now to extend this, so rewrite that negative z gamma of z multiplied by gamma of negative z. And if we write this in terms of our product series, then this is defined as follows. So it's negative z multiplied by 1 over z product series from k is equal to 1 to infinity of k plus 1 divided by k to the power z multiplied by k divided by z plus k. Okay, and then multiply with our input for negative z, so that this will be 1 over negative z, but I can just move the negative up top, so it's negative 1 divided by z of our infinite product, k is equal to 1 to infinity of k plus 1 divided by k, and so over here the exponent is going to be negative z, and then multiply by k divided by, so it's negative z plus k, so it's commutative with an addition, so I'll just move the k out front and then put a minus c over here. So now I can actually just simplify this out. Negative z multiplied by negative z, that's going to equal just 1, so I'll get that this is 1 divided by z of the same thing, k is equal to 1 to infinity, k plus 1 divided by k z, and then k divided by z plus k, and then let's see, so this will be z over z, so that's 1. So then multiply with our product, our infinite product, and this is k plus 1 divided by k to the power negative z, and then k divided by k minus z. Now this everything's under multiplication, so it's commutative, so I can actually rearrange our terms. So this way I get that, and also because since these are both products and they share the same index, I can just write this under one product. So this is just one product with k is equal to 1 to infinity of k plus 1 divided by k to the power z, then multiplied by k plus 1 k negative z, and then k z plus k, and then k z minus k, or k minus z. Okay, now if I simplified this out again, so they share the same base, and so meaning using exponent rules, so z minus, and then multiple with the exponent, so z minus z is going to be 1, or no, I mean it's going to be 0. So then this whole thing, it just equates to just 1, and so we're just left with 1 over z, and then multiplied by this product. Okay, so let's see, so 1 over z, then the product z plus k, and then k z minus k, and so therefore this means we get that this is 1 over z multiplied by the product of so the numerator will be k squared, and then divided by, so this is actually just a difference of squares, so we get that this is actually k squared minus z squared. Okay, and so far that's actually just equal to negative z multiplied by gamma of z multiplied by gamma of negative z. Okay, so I'll just underline this in black just to reiterate what we have so far. So now, next, what I want to do is we're actually going to prove this little tool, now, well, it is a tool, but this is also the definition. So the definition of sine of z is actually equal to z times the infinite product of pi k square minus z square, and then divided by pi times k square. Okay, so we're actually going to be proving this little definition to help us evaluate the rest of this. Okay, so I'll just write this proof in orange this time. So, okay, so here's how the proof goes. So, the sine of z, if we can write this, we can expand this as its Taylor series. So, but I'll also write this in terms of limits. So let's see, so this is the limit as n approaches infinity of, so this is n, k is equal to 0, and then this is negative 1 to the power k multiplied by z to the power 2k plus 1, and then divided by 2k plus 1 factorial. Okay, so if we pay attention to this summation, notice that this polynomial in particular, it has a degree of 2n plus 1. So therefore, we can use the theorem, specifically the fundamental theorem of algebra, to say that there's a max of 2n to the power 2n plus 1 roots. So there's a max of 2n plus 1 roots. Okay. So therefore, we can actually write in this we can write it as the following expression. So we can write this as a product. So this is b multiplied by the infinite series from k is equal to 1 of z minus a sub k. Okay, and then that's actually equal to sine of z. Okay. Well, and also define it such that the, let's see, a1 all the way up to a 2n plus 1. They're the roots of those polynomials. So the roots of, let me actually write a polynomial. Notice if z equals a sub m, okay, such that 1 is less than m, which is less than 2n plus 1 for any natural number n, it can be rewritten as the following over here. So this is a sub m minus a sub m, and then its product can be rewritten. So our upper index is m minus 1, and then starts at k equals 1, a sub k, and then multiplied by our product. So that means k is equal to m plus 1 all the way up to 2n plus 1 of z a sub k. And then therefore you can see that this is actually just equal to 0, and that's supposed to be equal to our sine of z, or rather, that's our sine of a sub m. Now for sine a sub m is supposed to equal 0. Okay, so then that means we can actually build our following set. Set a sub m is just equal to k times pi, such that negative n is less than or equal to k, which is less than or equal to n, for k can be any integer. Okay, so this means that this actually has 2n plus 1 elements. That's the set negative n plus 1 all the way up to -1. That has n elements, and also define the following set n plus 1 all the way up to 1. That has n elements, and then the singleton 0 is just 1 element. So therefore, we can clearly say that our sum from k is equal to 0 of -1 to the k, and then z 2k plus 1 divided by 2k plus 1 factorial. So this definitely has 2n plus 1 roots at max. And therefore, we found all our roots in conclusion. So now let's actually keep going in, rewriting our sine of z. So let's see. We said that sine of z is actually just equal to our, given that our limit from the Taylor series expansion, -1k z 2k plus 1 divided by 2k plus 1 factorial. So that means that can be rewritten as b times z of our product, such that our index k is in the integers, excluding our singleton set 0 of z minus k times pi. And so when we do this, we can actually rewrite the product series again. So that means this is rewritten as b times z of our, so it's k equals 1 all the way up to infinity of z minus k times pi, then multiplied by z plus k times pi. And of course that's actually just equal to sine of z. So now if I expand this out, then you can see that this is a difference of squares. So this is b times z. So this is, what is it, z square minus k square pi square. And then, so that's all we have so far. So now we actually have to find our constant b. So now note that sine of z approaches z as z approaches 0. Okay, so when we use this, we can now say that that means over here this is z is equal to b times z, and then our infinite product k is equal to 1 of so let's see, z squared approaches 0, so that means this is actually just negative k squared pi square. Okay, and then we could do some algebra here, but I'm just gonna skip some steps. So we're gonna get that our constant b is actually going to equal to our infinite product of this reciprocal. So this is -1 and then k squared pi square. Okay, and then we'll just substitute back to b for over here. So that means this is z times our, let me actually write it like this. So I mean this is z times the infinite product of -1 k squared pi square, and then multiply with our product from, what is it here, so k equals 1 of z squared minus k squared pi square, and then just combine everything together. So then we get that this is z, and then multiply by the product, the infinite product, and now we have a negative, so I'll when I distribute this, I can actually just interchange since this is commutative with addition. So that means this will be k square pi square, and then minus z square, and then that's just being divided by k squared pi square, and so that's just equal to sine of z. All right, cool. So we prove our little tool. So we're gonna use that to calculate the rest for the gamma. Okay, so now that we have this, let's actually write our sine of z in terms of like the Euler def of our product, and take its reciprocal both sides. So that means I'll get 1 over sine of z, and that's equal to let's see, so then if I take its negative reciprocal, this will be 1 over z, then multiply by our product. So this is from k is equal to 1 of so this will be k squared pi square, and then divided by k squared pi square minus z squared. Simplify this out, I can just divide pi squared down below, so then this will be 1 over z, and then pi, infinite series, this will just be k squared, then divided by k squared minus z squared divided by pi squared. You can clearly see that this is actually equivalent. So when we rewrite this, so that means our new input would be pi of z. So we'll get this little format here. Then you're gonna see that this is actually equivalent to 1 over z times pi, and then multiply by our product. K is equal to 1 of k squared divided by k squared minus z squared. But if you notice, we just showed that 1 over z multiplied by this product is actually equal to negative z times the gamma of z multiplied by gamma of negative z. So I can just substitute this back, and so that we get this as negative z, gamma of z, gamma of negative z, and then divided by pi. And we showed that negative z times gamma of negative z, that's equal to our product of gammas. So we'll just replace this with gamma z multiplied by gamma of 1 minus z, and then divided by pi. And now the last thing is just multiply pi to both sides, and we get that our final answer is gamma of z multiplied by gamma of 1 minus z is equal to pi divided by sine of pi times z, like so. And that is our final conclusion, drawn in this black box over here. Alright, that's pretty cool if you ask me. Also, once again, Merry Christmas to everybody.